So now, day 6 is all about applications. All right? So up to now, we're just learning the rules of exponent laws. We haven't really applied it to anything. All right? So I purposely left all the applications to the very end. Some teachers do it as you do it, learn the rules. But I figure, hey, focus just on the rules and we'll talk about the applications at the end. All right? Now, exponents show up in lots of different places. One of the places you're familiar with from last year is in formulas for shapes. Right? So last year you looked at cubes and squares and rectangles and triangles and circles and 3D versions of all these shapes. There's exponents involved. We sort of skip over, most teachers, how the exponents work. All right, but we're going to talk a little bit more detail about the exponents this year and some other spots as well. So we're going to sort of focus on where these exponents applications are. From this point forward, for most of you guys, there's not going to be any more units on shapes, depending on which math you go on to next year. Right? So shapes do show up in all your courses going forward, but it ends up being just like a one-off question. So you're applying whatever theory you're doing and there'll be some sort of shape involved. For the grade 8, you spent like a month working on shapes. That is not going to happen again. All right, so today is we work with shapes, all right, for some of it. Okay, now, one of the shapes you worked with last year was a square or a rectangle. A square has all the sides of the same length. So remember, a little line like this means the sides are the same length. Do you guys remember how do you calculate the area of a square?
I think
Lincoln? Yeah, length times width. That was the general formula for a rectangle. And a square is just a special case of a rectangle. Riley?
like x to the power 2.
Yeah. So we're going to talk about that. So both of you guys are correct. You said length and width. Since squares are both the same size, I'm going to say length and length, right? So the area of a square is length times length. Yes. Okay. So length times length. That's the formula I taught you, or your other grade 8 teacher taught you. That is actually an exponential formula, right?
You can say length exponent 2.
Yeah, so that's where we're going to. Here, if you did some of the extending questions, you would see that, hey, the base is what's being repeated. That's the L. How many times it gets repeated is the exponent. L exponent 2. And some of you guys already mentioned that. I already saw that, right? So this wasn't presented to you like this last year. But I just want to highlight the fact that it's an exponential formula. Last year, you're just focusing on how do you do all these calculations with these shapes. This year, the focus is more on the exponents. Now, if you realize this, the units start making more sense. When you did area calculations last year, what did the units always look like? Right? They always had some sort of the same shape. Centimeter something, meter something, feet something. Square. Right? Why is that? Because we have, say, a centimeter. Centimeter times centimeter. What's the unit? The base stays the same. There's 2 of them, centimeters squared. Or that's why it was always feet squared or yard squared. Because we're multiplying 2 of the same thing. And the same thing applies to volume. When we did volume, the equation was like length times width times height. Find the area here and go all the way around. Right? If we talk about a cube, that's all we're going to be talking about this year. All the sides are the same. Yeah, length times length times length. So the volume of a cube is length, that's our base, to the exponent 3. We repeat it 3 times. And this is for the same reason for the area. This is why volume always was cubed, centimeters cubed, meters cubed, feet cubed is a centimeter times centimeter times centimeter. And that's where it came from, right? So this year, focus on exponents, right? We're not going to do as hard of calculations. Now, the other one is to find the surface area of a cube. What did the surface area of a cube mean? What are we looking for? It says it in the words, but I'm not sure if everybody understands. Right? If I ask you to find the surface area of a cube, what am I asking you to find? Here's a cube. What am I asking you to find here? What do you do? Yeah. And so the area on the outside. Now on a cube, all the sides are the same. So you have this side here, and all the sides are the same. So you go, okay, I figure out how big this side is, then multiply by how many sides there are. How many sides are there? 6. So you go, okay, 6 times whatever this area is. So I go 6 times, well, how do I figure out this area?
Length times length.
Length times length, or length squared, right? So we're going to write it in exponential form, right? Sometimes you'll see S for side squared or something like that. I try to avoid S's. Sometimes my S's start looking like 5s, and that can be kind of a little confusing, so that's why I'm sticking with the L, right? All right. So now let's put this to use. Some people have a hard time doing questions without a diagram. So if that's your situation, draw the diagram. Here, what is the surface area of a cube with an edge length of 3 meters? So I'm going to draw myself a cube. So start off the square, then shoot off some lines going back at an angle. All right, and it says the edge length is 3. Okay. So what is the surface area? So we go to the formula. Which formula are we using, Malik?
I'll use volume cube.
Not volume. It's asking for surface area, so we have to use the surface area formula.
I think if 3 times 6. Yeah.
Yeah. So we want to use this formula here, surface area. So we get lazy as we get higher up into the grades. All right, you don't want to write as much. So instead of writing down surface area S dot A dot, I'm hoping your last few teachers taught that. Start off with writing down the formula. Don't go straight into putting the numbers in. Right? This is your communication aspect. Oh, this is the concept I'm using. Next step, these are the values I'm going to use in my concept. So I'm using the value 3, like Ryan said. So I go 6, where I see a L, I'm going to replace the value 3 squared. Or 3 times 3. I'm not going to dock you marks if you go back to the grade 8 way, but I'm going to show you how it goes in the grade 9 way. So now this becomes just a BEDMAS question. All right?
So
Calculate. Yes?
First of all, we should write the formula of that.
Sorry?
First of all, we should write the formula.
The full
Formula.
formula. Yeah, start off with the formula, right?
We should write it.
Yeah. Yeah, don't go straight into writing just the numbers. Right? So now we want to do our exponents first. So we want to do this calculation first. What number do we get? 9. Thank you, Max. 9, and we have 6 times 9 and 54. Right? And if you gave me 54, I'd give you almost all the marks. I'd take off half a mark.
Square. Cube.
Squared. Not cube, right? Because here, Malik, right? This is the formula we're using. Length times length. The unit's squared, right? So area, doesn't matter if you're finding area of one side or all the sides, stays the same, right? So squared, and the units for this is measured in meters, so meters squared. That's it. All right. Okay. More formulas. So last year, you were given a triangle, a special kind of triangle. It was a right angle triangle. It had a little square in the corner. What did that square mean?
Right angle.
Right angle. What does a right angle mean? Kirsha?
It's a big 9.
90, right? So then we label the sides A, B, and C like this. And it didn't matter if you mixed up sides A and B, but C was really important that you got it right. What was the C side?
It was, I don't know what it's called.
But what is it? Okay? So, what were you going to say? Sorry, I cut you off.
I was going to say, like, A squared plus B squared equals C squared.
Okay, that is the relationship. A squared plus B squared equals C squared. But what is C on a triangle? I'll go for Riley this time.
The hypotenuse.
Hypotenuse. So the C is really important because you can mix up A and B. C is called your hypotenuse. And it's the longest side. Right? And it's always across from this little 90 degrees, right? It didn't matter about the other two. We called them legs last year, right? If you mixed up A and B, it didn't matter. But C was the longest side. So we used this relationship. You remember what it's called? Riley?
The Pythagorean theorem.
Pythagorean theorem, right? It connected up. It says, hey, this square plus this square equals this square. Right? Did you guys see the water demo for this? I know I showed it to my students. Right? No?
I think we learn it in grade 8.
You guys don't know the water demo? Let's see if we can find it. Let's go here. Water demo Pythagorean. Oh, there it was. Right. So it really highlights how it works.
This season, Vistaprint has everything you need for your holiday night. And with up to 40% off,
Skip. All right. So you take the squares off each side, you add them together, becomes the same amount of space as the other one, right? There's a bunch of you guys in here from last year. I sort of showed you that, right? And it doesn't matter how long the sides are, as long as it's a right angle triangle, this relationship holds true, right? Right? So you find the squares, add them up, equals this square, then you had to do the square root. Because then you had the square root tells you how big each line was. You guys remember that last step, right? Okay. So we use this relationship if we want to find the longest side. But what if we wanted to find one of the shorter sides? There's a different relationship. So very similar to this.
I
Right?
think C exponent 2 subtract
Yep.
the
Thank you.
A exponent 2.
So the other way this formula goes, C squared, your biggest squared. This time we're subtracting one of the other smaller squares
That's one we have.
equals the other one. So we use the top one if you want to find longest side. And we use the bottom one if you want to find shorter side, right? The two small ones add up to make the big one. If you want to find the small one, big one minus the small one equals the other small one, right? When you do that calculation, you just got to do the square root, right? Okay. And there was another formula that involved a circle, and you guys had to find the area. And that was just area of a circle was equal to pi times r, or pi r squared, like this. It means the same thing, right? Another spot where exponent showed up, right? Okay. So let's put this to work. Okay, so here we have not a nicely scanned in diagram, but it's okay. We have a triangle, a right angle triangle with a square off the top of it that is asking you to find how long this side is. All right? What formula do we use? Right? A squared plus B squared equals C squared. So the information we're given is 9 and 12. Both these numbers are on the triangle, so we need to use a triangle formula. So we have, write out our formula, A squared plus B squared equals C squared. So I'll put a little C on my diagram here to label that side. Then you just stick the numbers in, 9 squared plus 12 squared. See, it doesn't matter which order I do the 9 and 12, right? equals c squared, right? So 9 squared is 81, 12 squared is 144, right? You add those two numbers up, 225 equals c squared. Okay, we're not done.
Yeah, I know.
That's c squared. So do you know what is the square root
Yeah.
of that? Do you know that one?
Yeah.
You've done that one a lot, right? So what number would that be? Riley?
15.
Yeah, because we've done that one a lot. 15 times 15, or 15 squared is 225. So you go, c is equal to the square root of 225, which is 15 centimeters. So this is 15 centimeters. Okay, so then we can say, hey, the longest side is, or that triangle is 15 centimeters. Now, I can almost guarantee you, you're going to get a question just like this next year, but it's going to be phrased slightly differently. They'll be looking exactly the same, but next year they'll go, what's the perimeter of this shape? So what does the word perimeter mean? Outside line. So distance around the outside. So you have to do the exact same steps as what you just did. Then you have to add up all the sides along the outside. Since this is a square, we have, so we're going to do a little side calculation. This is 15 here, that's 15 here, that's 15 there, right? So next year we'll be like, hey,
So,
I can almost guarantee you get this question. What is the perimeter? Give me a second here, Ryan. So you add up all the sides. So you pick a corner and you just work your way across around. You have 12 plus 9 plus 15 plus 15 plus 15, right? Right, so you add up all those numbers. 12 plus 9 is 21. 3 15s are 45. Yes, Ryan?
can I come? Yeah, I want to show you something.
Okay, sure. Come on up.
Can we write just these numbers? Like this number, don't write this part, this part. don't
No,
write-
show me the relationship.
Oh,
Start
just show
off,
it.
start us with the formula. Right? What are those numbers doing? So yeah, 45 plus 21, we got 61.
You should write perimeter.
Oh, they did it. No, 45 plus 21, 66.
Sorry, you should write perimeter too.
Yeah, so this wasn't part of the original question. I just want to put it on here because I know many of you guys are
It's
going to
optional?
do pre-calculus
It's
next year.
optional. It's optional.
Mm-hmm. It didn't ask for it, but since we're doing it, might as well talk about it, right? Okay. Let's skip around here. Let's go to the back page, and I'm going to skip around the back page. Okay. So let's go to do example 5, bottom left-hand corner first. Okay. Another spot that exponents show up is in reproduction, right? So a lot of bacteria and cells reproduce in an exponential pattern, right? So when they're doing predictions for how bad the flu is or how many cases of COVID there are going to be in a couple of weeks from now, they have an exponential formula. And we're going to create a formula today, right, which is a slightly simplified version of what they use to forecast how bad the flu season is going to be, right? So what happens is when you have any kind of cell growth, it starts off slow, then they start reproducing and it starts going like this. And this is called an exponential growth because it just shoots off, right? And this is a family of curves, right? And you're going to do a lot more work with that in grade 11. So grade 9, grade 10, you just start getting introduced to the idea. So today, we're going to create the formula that shows us this path. And all they do is then they graph it. You go, oh, we are here on this graph. In a couple of weeks from now, we're going to be here. And that tells us how many cases we should have, right? So let's get started here. Okay, so this question goes, we have a bacterium that is known to triple every hour. That's what it says. Triple every hour, right? So that's how it reproduces. It triples every hour. And the only other piece of information we need to know is how many bacteria do we have to begin with, right? And it says we start off with 50 bacteria. So now we got a bunch of questions here, And it says, okay, how many bacteria will there be after 3 hours? How many will there be after 5 hours? And this one's, can you come up with a general equation? So if somebody just tells you, hey, how many bacteria will there be in 30 days? You can just plug in the number and it'll calculate it for you, all right? So let's start off with, because we need to create this formula. So at the beginning, we start with times 0, right? And there are 50 bacteria. Yes? Ryan?
No, I don't have.
Oh, yeah, okay. Put your hands up. Okay. Then, 1 hour later, how many bacteria would you expect there to be?
150.
150. And Malik, how did you do that calculation?
50 times 3.
All right. So, we're going to write down that calculation, right? Because in terms of creating a formula, we need to see what the pattern is. And looking at the calculation you're using will help figure out the pattern. So Malik had it right. You go 50 times 3 equals 150. All right? Now, next up, we go, let's go 2 hours. Okay? After 1 hour, we have 150. How many bacteria do we expect after 2 hours?
450.
450. All you did is triple that previous number, right? So we could go 150 times 3 gives us 450. But to help with the pattern recognition, let's replace that 150 with where that 150 came from. That 150 came from 50 times 3. Right, so I'm going to rewrite this. I'm going to rewrite it. So instead of the 150, I'm going to write down 50 times 3. Then I still have that tripling for the second hour, and it still equals 450. Okay. Still make sense where all these numbers are coming from?
Yeah.
Right? That's why I like color coding, so that helps highlight where the number is coming from. Let's switch to purple. Now, after 3 hours, how many bacteria are there going to be? 1,300. And how did you come up with that number? You just triple it. It's not quite 1,300, is it? 1,350. So we could go 450 times 3, which is 1,350, right? And anybody should be able to do this. Coming up with the formula is a little bit trickier. So if I give you this question on a test, I expect you to be able to do this. You may not remember the technique to figure out the formula, but this should hopefully help. So now, where did the 450 come from? Let's just write it out. It came from this. So it came from this 50 times 3 times 3. Then we tripled that 450. That was the purple, and it equaled 1,350. Right? So we can say after 3 hours, there's 1,350 bacterium. That's our answer there. Okay? So now, we can just keep this pattern going. All right, you go, hey, how many are there after 5 hours? Oh, we got to take 1,350 and triple it. That gives us 4 hours. Then you triple it again, whatever that number is, that's for 5 hours. All right, we can do that. But do we notice a pattern creating when we look at these previous things? Do you see a pattern to connect the equation with the time? Malik, what do you see?
They all got 50 of them.
They all have 50. So we start off with a generic thing. They all have 50. Okay, that's our constant. What else? What else do you notice?
Every second one, it's a 4 in the start.
A 4? What do you mean by a 4?
Like, the 4 starts the number of the second time. Or, never mind.
No. All right, so look at,
You should multiply.
so we've talked about the 50s. Okay, that's fine. Next, what's left?
Exponent.
Are the 3s. Riley, how are the threes changing?
For every hour, there's another 3.
For every hour, there's an additional 3, right? So, look at this. For 1 hour, there was 1 3. For 2 hours, there were 2 3s. For 3 hours, there were 3 3s. Right? So, if I wanted to calculate 5 hours, I go 50 times, how many 3's would I put in
3
there?
exponent 5.
3 exponent 5. Well, 3 times 3 times 3 times 3. So you don't need to do the pattern. We figured out the pattern. Right? So now we can just grab our calculator and do it. All right? So I grab my calculator here and I go, turn it on. I go, okay, bed mass, exponents first. 3 exponent 5. I figure out this number and I multiply it by 50. And it's 12,150. 12,150. So we know there's 12,150 bacterium. Okay. So now, if you want, you can just keep that pattern going. You can find the formula hard. But I could say after 20 hours how many there are. And keeping that table growing, it's a pain. You want to be able to create this. So what is the general formula? How does it look like?
I know.
All right? How does it? Ryan?
I think for n, we should write 15 times 3 exponent n.
Excellent. So now, this is our general formula. 50 times how many 3's we have, where n is time. Okay? N is time. And that's a general letter we use for time, is the letter n. So after 1 hour, n is 1. After 2 hours, n is 2, right? And if this is an equation, we need something it equals. What does it equal? This equals our bacteria count, number of bacteria. So we create an equation, right, that predicts how many bacteria there is. Right, so this is sort of like the forecasting that they do for flu viruses. How bad is it going to be? So they get, what they do is they get sample data. They test people and go, okay, it's going like this. And they figure out how quickly is it reproducing. So that in a couple of weeks or in a couple of months from now, when the flu season hits, how bad is it going to be? Right. So the actual formula is slightly more complicated than this. This exponent becomes a fraction. And you learn that about in grade 11. So that's basically it, right? You can, at this point, you can understand. If there's somebody put it out there, you can sort of understand it. So our general formula is 50 times 3n. So 50 is our start population. 3 is how fast it reproduces.
Yeah.
And they all follow this format. So if I give you a completely different question about bacteria, and I said, hey, this time they start off with 2,000 bacteria and it doubles every hour. New question, right? Let's go new question here, right? And let's do a little blank spot somewhere. I don't know, find a blank spot in here. So let's do just a little spot here, right? Start with, let's say, no, I said 2,000. Let's change it to 4,000 bacteria. And it doubles every hour. What's the formula that predicts its population? How does it look like? It's going to look just like this. You're just going to put the right numbers in the right spot,
Yeah.
right? So what would it look like, right? Right?
3,000 multiplied by 2 to the exponent n.
Yeah, so we have to start off with our first number is our starting population. That is 4,000.
4,000.
Doubles means 2, right? And then we have our n, right? You could go after 1 hour, see it, after 2 hours, see it, after, then look at the pattern, create this, it'll come up with the same thing. So everything, bacteria-wise, sort of follows this pattern, okay? So now, not bacteria related, but science related, but a very similar formula. We have a number times a letter to the exponent 2. So this is a formula for how projectiles travel, which you'll learn about next year in science. Right? So this is how projectiles travel. They always travel in a parabolic path. So if you look at you throwing anything, they always go like this. And there is a formula for all of them, right? And based off of time, you can figure out how far the ball you've thrown has gone. So you threw a ball, Malik threw the ball, and in 10 seconds we can figure out how far away it is from them, right? So there's a general formula. You're going to learn more about it next year, and that's it. So when you get formulas, students get discouraged, and I mentioned this earlier. Like, oh, this is so hard. Even if you don't understand what's going on, right? They give me your formula, and then give you a number to put into this formula, right? So here is our formula. It says, hey, this is for a skydiver jumping out of a plane. Calculate the distance the skydiver has fallen after 2 seconds, after 4 seconds, right? So you start off with, doesn't matter if I'm talking skydivers or a cannon ball being launched and stuff like that, they're going to give you a formula. Start off with writing a formula. That'll at least get you some marks. You showed me the concept you're using. Next part is you're using that formula, just like we did with all other ones. You're plugging numbers in. The number they gave us is this 2s, right? Now, only has one of 2 spots to go in for. It can either go in for the D or it can go in for T. T. T stands for time. 2s is 2 seconds, right? So where we see T, we just replace it with the number 2. So we have 4.9, right? Instead of T, I'm going to put the number 2 in, squared. That's it, right? So now, we calculate bed mass, exponents first, right? So 2 to the exponent 2 is a 4, and we have 4.9. Right? So we have 4.9 times 4, and I can't do that in my head. Max, do you have that one done?
What? Oh, 19.6.
19.6, thank you. Now, with all these calculations, like time was given to us in seconds, 19.6, did you fall feet, kilometers, yards, how far did you fall? It'll tell you in the question.
Meter.
Right? Riley? Meters, yeah. So in the question it says, hey, distance is measured in meters. That's right here. So this is 19.6. Now with all word problems, I didn't do it before because I was trying to get more notes down. We can just say, hey, give a little sentence. The sky diver fell 19.6 meters in 2 seconds. Right? Okay, now pause it for a second. You calculate for 4 seconds. So start off with the formula, put the number in, calculate what the number is. I'll put up the answer on the screen here so you can double check your work. All right, so stand up assembly 8.4 meters. Now, the hard thing about this chapter, unlike junior grade and stuff like that, I can't give you a single way that all these questions are going to look like. Right? There's no generic way. All I can say is all these questions are going to involve, for the most part, exponents of some kind. Right? So you have we had this question. Right? We talked about finding the side length. And the strategy was just use the formulas for the shapes over here. For this one, we had to figure out our own pattern that came up with the equations and stuff like that. And here, we're just applying a formula that they give you. So either you're going to apply a formula you're given, or you should know, or come up with your own equation. Right? And that's the only general advice I can give you. So here's the next one. Right. No general formula here. We got to come up with it. It says, hey, you have a byte combination lock. Right? How good is the lock? How many different combinations can you have with this lock? So you have a byte combination lock. It has 4 numbers. And so you got one of those little dials, and each number can go through 0 to 9. And the largest combination is 999. So let's draw a quick little picture here. Right? So here's my byte combo lock. Right? So I have a slot here for numbers. I have a slot. Oh, let's do it in different colors. Slot here for numbers. I have a slot here for numbers. I have a slot here for numbers. And I have a slot here for numbers. Right? So each one of these dials can be 0 to 9. 0 to 9, 0 to 9, 0 to 9, 0 to 9. Okay? The question is, how many different combinations are there? So the lowest number is 0 to 0, highest number is 999. Yes?
10 to the power 4.
10 to the power. Okay, do you know how you came up with that?
Because there's 10 numbers. It might not seem like 10 numbers, but there's 0, 1, 2, 3, 4, 5, 6,
Yeah.
7, 8, 9. It's 10 numbers.
Excellent.
And you're timesing that by the next number, and the next number, and the next number.
Excellent logic, right? And if somebody don't see it very as quickly as that, I'll just use Malik's thought pattern and just add some diagrams to it to maybe make it so everybody can understand. So the first one. So suppose this one was only a lock with 1 dial, and Malik said, hey, it can only have 10 combinations, right? 0 through 9, that's 10 digits, right? So that first dial can only have 10 combinations. It wouldn't take too long for a thief to figure out how many combinations are. Just cycle through 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You're done. Right? Now, if we had another dial, all of a sudden it becomes a little bit more complicated, more combinations, right? And what Malik was saying was, hey, the first dial can be 0, 1, 2, 3, going all the way down to 9. So there's 10 numbers there. Now, the second one also has 10 combinations. So your lock code could be 0 on the first dial, then another 10 possible things here. Right? Then you can have 1 on the first dial, then another 10 different possible numbers there. Right? And same for all of these. So if you only had 2 dials, right, it'd be 10 here, and how many here? How many different combinations are there, right? Right, so each one of these has 10. So that's, right, so that's 0, that's 10 combinations here. That's 10 combinations here. 10, 10, 10, 10, 10, right? So that'd be times it by 10, right? That gives us 10 squared. That's sort of what Malik said, right? All right, and then if you add another dial on, so we have 100 combinations. So if you have a 3 combination dial, so just the green one, each one of these 10s can have another 10 on top of it. Another 10. So we had 100 different ways of doing this. Now each one of those 100 different ways has another 10 ways on top of it, another dial. Right, so it is times it by another 10. Right? So now we're at 10 cubed. And with 4, it's going to be 10 to the 4. So there are 10 to the 4 combinations you can have. Right? Right? So that's proving it. It sort of makes sense because you can go from, actually, what number is 10 to the 4?
10,000.
10,000, remember? 10 times 10 times 10, 10. So that's 4 zeros. We're going to add to the end of this. Right? So it'll be 10,000 combinations. Right? Which sort of makes sense because you can go all the way up to 999. So if you include 0, that's right, 0, 0, 0, 0, that's 10,000 combinations. So you showed it, right? So this is how you're going to do like probability calculations if you decide to do it in grade 11. It's kind of fun. And this is intuitively you can figure it out, but you're going to get to blocks where you'll have numbers and letters. So how many combinations are there? You can't intuitively see it, but you got 0 to 9, that's 10 combinations. Then you have maybe A through Z, and there's 26 combinations there. But the possibilities are the same, right? 10 times 26 this time. You just figure it out. So that you do sort of if you take some sort of statistical math in grade 11, right? I quite enjoyed it. If you're going off to health sciences or business, you may end up going to that kind of math later on. Okay. Final question. And I think I might stop after this one. So you guys look tired, a bunch of students here. All right. So last question. I'm hoping you saw it last year, so I don't refresh your mind. You'll see this. You should have seen something similar to this last year. You'll see it this year. You'll see it again next year. The question is, hey, we have this shape. I want you to be able to tell me what is the area of the shaded area. So in the little corners, how much space is this shaded area? All right. All right. So if you're talking about area, have you guys seen that one before?
Yeah.
Or something similar? All right. Right. Talking about shapes, you have to work with shape formulas. What shapes do you see?
Circle and square.
A circle and a square, right? So we have a circle and a square. So how can we use a square and a circle? So I'll do the square in red, a circle in blue. How can we use that? Alan?
Oh, you can find the area of the circle using the radius,
Yep.
and then subtract that from the surface area of the circle square.
Yeah. So if we find, sometimes I cut this out. Do I have the scissors handy here? Right? Where are they? Oh, maybe they're up there. Put it back here. Right? If we have a square, right? Imagine this piece being a square, right? Yeah. Right? How does this go? Something like this. If we have this rectangular shape in here, right? You find that area. You find the area of the circle. You take out the circle. You're left with the tidbits on the outside edge. So when we say take out, that just means subtract. Right? So we find the area of the square, we find the area of the circle, and we are going to subtract those two areas. Right? So now you can do this all in one line, but you can do it in multiple steps as well. So let's go area of square. The formula from the front side of the page is length squared, or length times length if you want to stick with the grade 8 way. How big is the length? Riley?
16.
16. So 16 squared. Does anybody know what that number is? Riley?
156.
Thank you. 256. and centimeters squared. Okay. Now, we have the area of the circle, and it's pi r squared. Now, in grade 10, your teachers start to encourage you to use the pi button on your calculator. In grade 9, I'm fine with if you use the numbers 3.14. As you get a higher grade, you want more accuracy, so the pi button gives you, I don't know, like 10, 12 decimal places. But if you don't want to learn how to use the pi button, you can use that. Right? Now, to use this formula, we need to know what r is. What is r?
8.
8. R is your radius. Thank you. And the radius is the distance from the middle to the outside edge. If all the way across is 16, halfway across must be 8. So, times 8 squared. So, we have 3.14 times 64. And grab a calculator. 3.14 times 64, and I get 200.96.
We round it to 201, or?
So this year is not so bad. Next year, you're going to start talking about rounding rules. And generally, you don't round until the very last step of your calculation. So you're going to have to be storing things here. This year, if you rounded it here, I wouldn't mark you wrong. But the question says give your answer to 1 decimal place. So I'd keep it going like this to the very end, and then round the very last answer to 1 decimal place. So shaded area is just subtracting these two numbers. 256 minus 200.96, right? So that's going to be 55, sorry?
55.04.
Yeah, 55.04 centimeters squared. And that's it.